Hello and welcome to another exciting edition of CG Game Development. I am your host, Nate Nestler, and for Hyperactive Studios. Now, this particular one, we're getting ready to do something a little more exciting here. We're going to go into doing the pixel shading, not just do the vertex shading, and then we're going to move into the world of textures here and get some good old PS1, PlayStation 1 type graphics here. But what we're going to show, what you can do with some of the capabilities with some mathematics, stuff in the color in the very next video after this, is really fun and exciting. And so there's all kinds of things you can pull off. And we'll start to get a little more exciting with this video right here. Okay, so first of all, I've loaded in a model. Now, you can feel free to do this too if you like. I talked about you can load in models earlier. And what I did is I downloaded a model that was a 3DS model. And all I have to do is then select the model and say open, which is precisely what I did, and I got this model here. And also brought in the texture automatically with the 3DS format. And now you're probably wondering, where did I get this model? Well, you can actually download these models for free, thousands of models actually for free, online from archive3d.net. Basically, we have a whole bunch of people from the architecture industry who don't want to reinvent the wheel every time you turn around to a building visualization. It's pointless. I mean, just who cares if you own that particular door or that, it just doesn't matter. The main thing is to reduce costs and make it more cost effective and manageable. So that's pretty much what they've done, and they've just released all kinds of assets. You see the number of models you have per page here, right? Well, you got 300 pages, and then the next 300 pages, it's about 900 something pages if I remember right, on here. So you get the idea. There's several thousand models that you can work with here to play around with. And so in this way you can load in artist models and get an idea of how your shading techniques are working. Now, not all of them come with the textures like they should or whatever. So you'll have to play around and find the ones that work well for you. And the scale is completely, varies completely depending on what program they made it in, or did it on the exporting, did it suddenly scale up the units like crazy, or did they make it ginormous and didn't realize it, or who knows. There's so many different things that could go on to make them ginormous or super ridiculously small, or you name it. So don't expect any kind of consistency between scale here between these models. But I downloaded this fighter model one. I just went to the aircraft here under the filter and then hit filter in order to pull up these models. This one doesn't have textures. It looks really cool, but it doesn't have textures. So if you pull up this one, it has a texture on it. Now these are just simple textures, and thankfully also FX Composer 2.5 comes with its own set of textures too. And that's important and extremely useful, needless to say. Is definitely a much needed thing here. If I go ahead and select textures, I can see some other textures that I've loaded. Now if I want to load some more textures in here, it's no big deal. It's quite easy actually. All you have to do is come in here and say plus, and then go in and select the texture you want, and then it'll load in the texture. Here we've got a normal map, a color diffuse map here, a gloss map for doing specular highlights. Here's a reflection map. Here's another one for color diffuse map here for this spaceship thing here. Very cool, and all this wonderful stuff you can do here. This is only a 512 by 512 model, and this lets you access these textures to be used and applied into this model, or any other model for that matter. In this case, right now we have our our teapot here with its own set of layout. Alright, so let me just apply the other shader to this, because we don't want... Yes, there it is. That's the one. So I just need to drag and drop my shader to there. Okay. Like, all the pretty colors went away. Yeah, well, this is a little older shader, so here that I coded just a second ago, just to show off this effect here quite nicely. And if I go in and I start moving around, okay, again, we're getting the same coloration that we expected from before. Very cool. So how do we do with this? Okay, so what I did was I set up we still have our structure from before for our VS material, so nothing's changed there, but we have a struct now for our pixel shader material shader. And I've done a const also for this because I'm making it a uniform. I'm doing a float 4 here, and then color colon, and then color semicolon. So here we're going to be accessing the color, and we still have our diffuse color that's tied into this. But now we have a PS material struct here, a data type, and the main PS for our main pixel shader function with the actual pixel shader code in it, or fragment shader, depending on how you want to call it. Okay, so PS material, and then out here, semicolon, and then out.color equals in the diffuse color. Now remember, we get the diffuse color from up above here, which is this right here. And we're just saying that this diffuse color is equal to out.color, which is, again, the color value that's here tied into the color of the model here with our structure. And then when we return this out, it returns this color. Now I know there's only one variable in there, and so that's rather boring. Normally have multiple variables in there. And that's because I've done that in order to make way for better, more expansive textures here in the near future, including the one right after this, the texture one. So I figured keep it easy, keep it straightforward, and then build upon it so there's not like a whole lot of changes, make it easier for you to follow. So same idea with this. And I'm going to do a little spacer because it makes it look a little nicer, a little prettier. Okay, so good. Okay, so and then again, this color gets returned back to the shader and applied into OpenGL, and it gets applied to the actual model. So again, vertex shader right here, brings in the position and color, the position and color exported out, passed into the material. The material sets the color here, so yeah, we're getting the color set twice. We could remove this color one and just have this color one drive it, that's fine. And then return the out here from there. So here we're actually shading our pixels and not just the vertices. And it probably doesn't make a whole lot of sense of why we would do that, and it really doesn't matter on something this simple. But once we go to the texturing one, it does matter. Also, I want to point out some other profiles here. You'll notice some other profiles, and that is the FP30 one here. And that's going to be, again, for OpenGL. So OpenGL is going to use this fragment program here, 30, for older profile. And then you go into your PS_2_0 and PS_2_X for DirectX for another older format for it. FP20, again, OpenGL, an older format even yet, for supporting older cards. PS_1_1 and PS_1_2 and PS_1_3, these are all DirectX, going even older, for supporting earlier versions of DirectX and older technology, older cards. And then we have ARB FP1, which is your oldest one for OpenGL. And that's ARB, fragment program 1 here for your shader. And that'll put you on to the same compatibility as pretty much OpenGL 1 for that kind of shading capability and for those hardware that goes way back there and then at that point in time. With that, now you have your different profiles for your fragment and vertex program, and there's probably some newer ones even yet. You can always just check your documentation from NVIDIA for CG shading language straight from NVIDIA's website. We'll go over that sometime. And where you can find out even newer profiles and get a list of the hardware and specific things of that nature from NVIDIA. But for the meantime here, you can see that yes, it does pass the color directly through, and whatever we set it to, that becomes the color. And that's pretty much all there is to that shader. So let's move forward. And as you notice right here, this again, we're going to compile our FP40 profile here with our main PS, which is calling back to our function here, PS material main PS right here, which is our function for our pixel shader. It is our main function for pixel shader. Okay, cool. Now let's move over to the exciting world of textures. Now, in textures, we're mostly going to be worried about sampler 2D textures. And before I start talking too much, let me just slap on this one here. Yeah, I like this one. Alright, pow, there it is. Alright, and I'm just going to zoom in on this little, that'd be a shift and a left mouse. to zoom in on our wonderful little teapot here. Okay. And when I come in here, now one thing we haven't done is put in the normals for this teapot, and that's something I should have done. And we'll get into that later on. We'll do this in steps. We're just going to worry about the actual texture aspect of it right now, but you would want to have normals assigned to this model, and you can certainly see some problems by not assigning that to it. But for right now, this will get us by. Okay, so you see a lot of the same stuff as before. Okay, great. And here we have our text coordinate. Now, texture coordinates. You're probably wondering, what on earth are texture coordinates? Well, basically, there's no way to really... Okay, like, for instance, the world, the globe, right? It's round, but you can't lay it flat for a map. Yet we do. But it doesn't lay just totally flat perfectly like a picture on a wall. You know, it doesn't become a perfect rectangle. It gets all distorted and tore apart as they try to lay it flat, right? The same thing if you took like an orange peel, peeled it off an orange perfectly, and then tried to lay it flat. You can't. It's going to tear and rip as you try to press it flat. Same thing. We have to map these 2D images to a 3D model. And what an artist has to do, well, and there has to be some information, basically, to tell the computer how you're going to map this 2D image to a 3D model. And the way that is done is with texture coordinates. They're basically like X and Y coordinates going across the 3D surface of the model to tell where the pixel is going to go for the different color pixels of the image. And I can prove this a little better. Here we go. So here is our diffuse channel color map image texture, if you will, and it's getting applied to this spaceship here. Okay. Now, what's going on here is that there is a set of UVs, and if I were to go in here in edit mode, you can literally see the texture layout for this model as these different polygons get mapped to the 2D color of the image here, and this color is getting mapped per polygon and directly onto the model. So, and I can prove this. Say if I go ahead and select this and move it around, check it out. I'm manipulating those texture coordinates, and it's getting moved around all over the place, as you can see. And of course that doesn't look good. Not at all. Really, truly terrible. So, and this way we're mapping the UV coordinates. And you can see you can also manipulate these coordinates. Literally, you could just offset them and move them mathematically. And that's essentially what I'm doing graphically here. And you can do that inside of a shader too. But this is what I was talking about. Literally maps a coordinate system from an image to the actual model so that, you know, the model looks amazing. And one of the great things about Archive 3D is that this can be used for commercial and non-commercial purposes for those models on there. And so it's a lot more of a open, viable method for, you know, getting stuff done. But, okay, so I think I've already proven it to you pretty much that these actually do map. But just to prove it to you a little further, I'm going to just literally paint on this model here, and then when I paint on the coordinates, it's going to appear on the model. So, as you can see, there it is. It is literally painting right on the model accordingly. And that's because whatever I'm painting or doing here is getting mapped over to the actual model, and that looks terrible. I can also come over here and say, if I go into texture mode and go in reverse, say we were to map the 3D, whatever is being painted here, back to the 2D coordinate system of the actual image. Bam, there it is. You see it. It appeared right there. So hopefully that proves to you that we really are mapping these pixels from the image directly to the 3D model. And this would be with a 2D sampler, if you will. Basically, a 2D sampler is going to do the coordinate system, you know, X and Y, and find that particular point on that image to map it to the texture coordinate of the actual model, and that's what the 2D sampler does. So with that, now you can understand what the 2D sampler is and what texture coordinates are for and why we need them. Because I always like showing off things visually to make it just, I don't know, it makes sense. It hits home a lot better, I think, when you do that. So here I am inside of our simple material here, and the only thing we really need for our material for output after we're done is the actual color, because we're not really interested in any other aspects of the material and the output of it. Change things up a little bit on this, my apology, but I think it makes things easier and a little cleaner and makes a little more sense. So my VS material, I'm using this for my output for my vertex shader, which I then turn around and use for my input to my pixel shader, and then use this PS material as my output for my pixel shader to be applied to the model. So this helps, and I think simplifies things really. So over here, you can see that we have created a graphical diffuse color right here. And let me just show this off real quick, because this is really neat. And I can change, whoa, check that out. I'm changing the color of the image interactively. This is very cool. You ever seen those screens, you know, where you can go in and you can start making changes to the character, for setting up your character look and define your custom, setup for your character interactively in the game? Yeah, same kind of technique right here. We can use some mathematics in order to multiply colors by our images and things of this nature in order to colorize them, and thereby do stencils and things of this nature, masks, if you will, for the image in order to colorize it in different ways, and hop it up so you can have your like little Halo Chief guy or whatever, go in there and sit there and start tweaking the colors and everything for his armor and his suit, and you do this on the RPG games, and I could go on and on and on and on. You can even mix it up where you only have the color go into certain areas of the image and not other areas. And there's some tricks to this and everything. We'll start getting into that in the next video. It's very, very cool, though. It's a lot of fun. But here we can start using this color here to manipulate however we want. And then we could even use this, since it is being multiplied. And like I said, the mathematics matter. So see, if I turn it up here, we get the full color. If I start pulling it down, I start darkening this all the way down to black. And so this acts as basically an offset, or it is a multiplier. It acts as a parameter which you can usually use to just interactively control the look and feel of a particular art asset on the fly. And so for an artist or for game game players, I mean, people wanting to play the games, this really makes it really nice so that you can easily manipulate this stuff and get exactly the look you want. So awesome, great, and that's what we're looking for. Okay, so let's pop over and let's have a look at these shader programming. Okay, sampler 2D, color sampler equals sampler underscore state. Right here we have our texture, color texture. It's getting passed in, so we're getting a color texture from here that we loaded in, which is this image right here. We're loading that in. We've given it a name of diffuse texture, and the resource type is 2D. Now remember, this is an annotation, so that makes it easier to follow, so that it be displayed elsewhere to where it's clean and pretty. Alright, and you see it, diffuse texture. Okay, cool. And then this is the actual texture that's getting loaded in here. In this case, it's default color.dds that's being loaded here. So that's appearing here from this texture resource. Now, with the texture being loaded, then we load this texture image that we're going to be applied to the texture coordinates in our 2D sampler. So we set up a 2D sampler. We're calling it color sampler, and we call it whatever we want, just like we can call it this whatever we want to. And we're setting it to equal to a sampler state, and we're saying the texture is equal to color texture, which is this texture. So it sets up our texture here. Min filter, we're going to do a linear map linear semicolon, and so this is the minimum mapping, and we'll linear. Okay, well, this gets into something a little more complex. Okay, so in linear interpolation, let's just start going over it now. Interpolation is, okay, say you have, you've marked down, you're going to go from 0 to 1, right? Well, the computer with linear interpolation is going to figure out all the values in between 0 to 1 depending on whatever range you give it. Okay, that sounds really complex, but no, it really makes sense. just think about a gradient of color going from white to black. You get all these grays in between as it builds up to black, right? Well, one of those gradients, like in Photoshop or something like that, that would be an example of linear interpolation. You have one point on the screen here, and you have another point over here, and then you have a whole gradient of color all the way over. Let's see here if I can't just suddenly launch. Let's just launch GIMP real quick. This is an open source program, kind of like Photoshop. I have Photoshop on my other computer, but you can sit there and use this in order to do all kinds of art tools and stuff. And you can also kick out images and things of that nature that you need for doing your programming or whatever is required here. But let's see here. Let's grab the gradient tool real quick. Okay, so yeah, so you have going between black and white here, right? Okay, cool. And let's just say I drag and drop this image there. Bam, there's a gradient, right? So this is what I was talking about, linear interpolation. All we have is the input of black and white, right? But we're saying going from this point to this point, linear interpolation across that whole span of distance, right? So what it does, going from black here, the computer starts computing all the values in between black to white until it reaches this point here, and it's doing it in a linear fashion, so it's totally smooth, clean all the way across the actual span of distance here. You can have linear interpolation and also in 3D animation. So you're having for character animation, you could have two different keys for motion, and then that linear interpolation there is going to actually make the model move. I'll prove that real quick here. Let's just go ahead and switch this back over here to object space. I don't care. Alright. So I have this model here, and I can prove that I can sit there and key this real quick for doing an animation on this. So let's see here, what would be the easiest thing? Okay, cool. Let me just do this. There we go. Nice. Alrighty, so now that I have this set up here, if I just go ahead and key this position of this model here at this particular point in time, so I'm keying the location of this model. Great. If I do in here, you can see that it's actually been keyed. Great. Now, if I go ahead and grab this and move it up, right? Okay, we'll just move it into the darkness. Yeah, it's going through the hanger or something like that. I don't know, whatever. Okay, well, first of all, I need to do something a little more interesting. I need to set my time, right? Because although if I'm not putting in 2 different points for it to interpolate over, it doesn't know. It can't sit there and interpolate over no time at all, right? That doesn't make sense. Just like you couldn't have 2 values right on top of each other and then try to interpolate to them, it wouldn't work. Okay, so I'm going to hit I'm just going to go ahead and key this other location. Okay, great. So it's going to do a linear interpolation for the 3D program here between it, and it's just moving right up, just like that. And that's another linear interpolation. And this is the animation here. This is another example of it. So here we are at time 0, going all the way up to what, time 60, and we're just doing a linear interpolation across these points here as we move up to here, and it just makes it simply just move across. Now, did we key for every single frame of 60 frames all the way up to that point? No, we didn't. We only put in 2 keys. We started at this particular position, and we told it to end at this position, and then the computer, through mathematics, did linear interpolation all the way up to this point here. We're doing the same thing. We can do both in the shader. We can do it with time based for animation. We can do in linear interpolation for graphics, for the shading. We can do it for a lot of different things. And so there's so many capabilities, and there's so many different facets and things you can do with this, and it's very powerful. And it just, I don't know, it just opens up the realm of capabilities for whatever you want to do very easily to do all kinds of nice things. So there's 2 different examples graphically to show exactly what I'm talking about from a mathematics standpoint to a visual representation. And I like having visual feedback for everything we're doing, and so you see it, so it's not just theoretical. Oh, imagine in your mind what it may look like. No, I like actually showing you what it looks like as we do it. I think visual feedback with visual programming is very important when you're trying to learn it, because otherwise you just really have no idea what it is you're doing until you get in there, start messing with it, start seeing the effects of what it is you code. Then you really don't see what it is you're doing. And so try to show you as much as possible as we explain the different parts of this code, exactly what's happening graphically with each part of the code. Okay, so with that spiel, let's move on to that's a minimum filter, and then we have our mag filter. Mag filter means max. I don't know why, but they've been calling it mag filter for forever. They have it. It's called mag filter also in OpenGL. You see it all over the place. But mag filter, just think of mag as max. So max filter here. So we're just doing a linear here. Oh, by the way, mip mapping Boy, DDS file here. Let's see here. Do they happen to show the DDS capabilities here on this thing? I don't remember. Let's see here. Probably not. That would be my luck. All sizes. Okay. Well, yeah, I wish I had a way of showing you this, because it's certainly cool. Let's see if I can't do something real quick. I don't think it likes me running on Windows 7 like this. I don't know, I've been having trouble with Windows 7 on several things. Okay. Particularly with the textures. This program wasn't really written for Windows 7, it was written for XP and for Vista, so it was never compiled and coded for 7, so you know, you can have problems when you try to run a program that wasn't developed for the software you're running it on, more or less, and been running some issues for that because of that. So if you have Windows 7, you may run into some issues here and there when you're running this program, and just about any other program for doing shading for that matter too. So they're not alone. It's just an issue. If you're on XP or whatever, then you don't have to worry about anything. It should all work fine. But if you're on Windows 7, then you might have some issues, like I'm having. Okay, basically the way this works is, which I really could show an example of it, but it consists of many different images at different sizes going down. So this works with like level of detail, LOD. Basically, we're going to have a more detailed image as it's closer to the camera, and have less and less detailed images as it gets further and further away from the camera. Reason why you do that for performance, if you have a smaller image, then it eats up less on the 3D graphics card, the sample, and eats up less memory. Whereas if you have a larger image, it's going to eat up more memory on the card to process it and such. So thereby having it, with the DDS here, with the optimization due to the 3D graphics card. Now, if you notice right here, we got a nice special numbers here, 1024 by 512. Now, if you do, you can do totally square images like this, but it has to be a certain number, it's a power of 2. So, meaning it'd be like, 128 by 128, 256 by 256, 512 by 512, 1024 by 1024, 2048 by 2048, 4096 by 4096, 8192 by 8192, etc. Or you can have it to where it could be elongated, like for instance like this, where you have like 1024 by 512, where it got power of 2. So, it's still within those numbers, and you can have it be a rectangle, or, either elongated or tall, either way, horizontally or vertically. And that's fine, because it's still going to map out properly in memory and everything on the 3D card, and that's important. But, you could even go as far as going, like, say, 2048 by 512, you know what I mean? So it's 4 times, longer than it is tall. That's fine. You could do it 8 times taller, or 16 times taller, or whatever. It doesn't matter. You can do that. And it's perfectly fine. But you could have 32 by 32, 64 by 64. You could have 16 by 16, 8 by 8. I'm sorry, 16 by 16. I don't know if it gets much lower than that. I don't usually make images smaller than that. So anyhow, it starts getting to be a dot. I don't know what the point would be. But you can see right here the use of this for the color. So that's the whole point of a DDS image file format. It's really good for games. It's extremely fast and extremely efficient. It's used on a ton of games. There's a newer format we'll go over one day here that's really nice too out there. I don't know if it's compatible in this particular program or not. I would have to look into it. But DDS has been around for a long time, and it's excellent and it's very good. And that's what mapping is, with these different sizes for level of detail of images all stored into one image. And it only samples the one it needs. And so it doesn't sample and load into memory all those images. It only samples and loads in the ones it needs and not the extra ones. So that's very nice, and that lets you dynamically change the images, and the hardware's been programmed to handle it specifically very well, and it's just super fast and it's awesome. So that's the reason why DDS for the image. And that's how that works. Okay, So we also have our wrap SNT. So what's SNT? Maybe you've never heard of it. Maybe you've heard of UV. UV is our coordinates. So here we had our coordinate system here, yes, for our image. And say you had, well, let me just go back to creating another one of these here. UV image map, go ahead, pull up the texture here again. Okay, so U and V, right? So you don't know which way it's going to be. Maybe it's U this way and then V that way. It could be mapped different ways. It could be V this way and U that way. Doesn't matter. It could be either or. But it's going to be one way or the other. Well, okay, so from a technical standpoint, you can't actually change and manipulate U and V. They're hard-coded in. They're actual physical full size. It's 0 to 1. That's all there is to it. Pow. You can't change it. If you want to make an image repeat multiple times across a model, you can do that. But you have to do it arbitrarily through mathematics and then apply that to the UV. So what you do is you take the UV coordinates and apply them to S and T, where S and T maps to UV, meaning that U is S and V is T. Does that make sense? So if you have a variable U, whatever's stored in U goes to S, and whatever's in V gets stored to T. Then you can do mathematical operations on S and T, because you can change those, because those are variables that you created, and so therefore you can access them, and the standard is to call it S and T. That's what everyone calls them. Call it the same thing. That's what everyone calls it. I mean, everyone. So stay standard by all means. Don't make things more complicated and difficult. But we have our S and our T here, and then we can sit there and change these mathematically. And that's exactly what we're doing here. Okay, so we're mapping this stuff through S and T with a wrap here, and it can be repeated. Right now it's set to repeat. And then this allows us to graphically, or programming from a programming standpoint, change, manipulate our UVs where we can make it repeat many times across the surface with the texture across the UVs. So it's literally possible to shrink or blow up or repeat or scale images as they're, well, not the actual image, but the color information of the image across the 3D model, the pixels. Okay. So with that, let's have a little better look here. So we're passing in our values here, and so we need our text coordinates, right? So we need from OpenGL or DirectX for them to pass in our texture coordinates. And it's a float 2 because it's U and V, right? Two float values are getting passed in. And our position still here is a float 3 for position, and that's getting passed into here. We could do this in struct, but we didn't. VS material space out. Now remember, we had our VS for our vertex shader material structure here. And so we have our position here, color, and our text coordinate. So we're going to use this for our out versus our in. And we named our variable out here that we defined of type VS material. And then we do out.position equals, and then again we're just going to multiply it times world view projection coordinates. Float 4 here, we have our position.xyz, comma 1.0. Then again, this is going to be, well, it's pretty much straightforward, x, y, z, and then we're going to change our non-homogeneous coordinates, which are just x, y, and z, to our homogeneous coordinates, x, y, z, w. Again, we're doing w because we don't want to scale the, doing a 1.0 for our w, because we do not want to scale our x, y, and z to shrink the model or whatever. Over here we have our out.color equals diffuse color, semicolon. And so this just passes along our artist-defined color from our actual shader here, which is this one right here, a diffuse color. So again, this is our diffuse color that we set up as an artistically driven color parameter, and that is right here. And this is our annotation. Again, this is called an annotation, and all those values are being set to it. Okay, and then we have our out.textCoord equals textCoord. Now remember, we're passing our text chord for text chord 0. You're probably going, well, why does it say 0? That's weird. Well, you can actually have about 8 textures compiled on top of each other for a single model, and then you can layer them and do all kinds of mathematics to mix them, intermix them, do all kinds of crazy things, apply them to different areas. Like you'd have normals going for the normal map, and then you could have other ones for the diffuse map, another for ambient map, specular map. You can go on and on and on and on. And so you have many textures for a single set of texture coordinates. And the default in the fixed function pipeline in OpenGL is 8. But there's all kinds of things you can do. You can have multiple texture coordinates too. So that's the other thing, is you can have many different sets of texture coordinates. This is done quite often too. The reason why this is done in particular is, well, as an example, characters, 3D characters in games. Usually the head model will have totally different UV set than the body. Even if it's all one texture, you can have multiple UV sets for the different parts here. So the reason why they would do the face, because the face needs to be more detailed, because people associate with the face more. So faces always need to be more detailed on a character versus the body itself. Body's still important, but the face is even more important. It's the most important part on the person for a character. So typically you'll have a different set of textures for the face than you do for the rest of the body. And the eyeballs and stuff are included with the face texture and head texture, and the hair and all this fun stuff. It all gets assigned to that separately. And so you can have multiple UV sets, as it's sometimes called to artists, or texture coordinates. Okay, and that's what that's allowing. But we only have one set of texture coordinates, and we're applying our images to that single texture coordinate. So it's only one. Here we're assigning it to our structure text coordinate variable here, and we're accessing our text coordinate variable within inside of our structure with the dot operator, and it's equal to the text coordinates that we're passing in from the 3D model that's coming in from OpenGL or DirectX. Okay, great. Now all this gets returned out to that structure, and we're using that structure, we're passing it into our material. So like I said, we pass stuff out of our pixel shader, and then we pass it in to our fragment shader or pixel shader, whatever you want to call it. Here, well, one of the two. You can't call it anything you want. One of those two, I guess. VS material space in. We're naming our variable with capital IN so that we know that the structure here of the in variable is going to be values coming in to our pixel shader, and the ones going out of the pixel shader are separate. So that way it visually lays out very easily, recognizes, hey, this is going out, capital all out, and then capital in, hey, this is coming in to the thing. So just visually lets you separate it and make it easier for you to follow. Okay, so PS material space out. So again, this is vertex shader attributes that we're going out, coming into our pixel shader, and our pixel shader structure coming out from there with our out structure, well, with our PS material structure, which is going out. So we named the variable out for that. Out.color equals diffuse color times text 2D. So this is a 2D texture, and then we have our color sampler. Now here we created a 2D sampler. Yep, sampler 2D data type. We can have a sampler 3D and a sampler 4D. Sampler 3D lets you do 3D textures. Those are procedural textures. We haven't gotten into that. Not as used as much in games. I'll tell you what, most of the time, I would say 90-something% of the time, it's going to be a 2D texture sampler. That's going to be the main way of doing stuff. There's also a sampler 4D, which is going to be a volumetric texture. Think smoke, for instance. That would be a volumetric texture to be applied to a 3D model. And that is really nice and useful too. But once you start getting to 3D and 4D textures, they start taking up a lot more memory, and they start eating up a lot more resources for a game. So you don't see them as often. That's why there's a lot fewer of them. They do use more resources. So, and an artist can paint a 2D texture. And typically, an artist can get much better results with a 2D, texture by painting it up by hand than you ever could by trying to, do a whole bunch of mathematical effects and stuff, trying to recreate a realistic image. I mean, it's very difficult to sit there and use a bunch of mathematics to recreate a photograph when you can just paint one or take one from an actual camera and apply it to the model. So that's why. You don't see it as much. It's hard to get the quality level, and then it eats up a lot more resources on top of that. But it doesn't mean you can't intermix the two. So you can actually intermix 2D images with 3D texture coordinates, and then have both used together to create all kinds of crazy effects. And then since it's done procedurally in the 3D part, you can sit there and animate that very easily and cause all kinds of crazy cool effects to be animated in your shader. Like making lava flow across your shader, or making like fire break up through the model and animate as it flies across your model as it's like caught on fire or something like that. You can do all this kind of crazy stuff with it. And so then it all just comes down to mathematics and manipulating these textures coordinates. You'd be shocked what you can do with just literally, like I was making that image swim across the texture coordinates for that plane earlier on Blender there. You'd be amazed doing something like that will make it look like water is moving, or I mean, you name it. It's just moving and manipulating texture coordinates with an image can really make a big difference too, to make it look like it's being like something's actually happening. And it's just a really quick, cheap effect that you can sit there and do, and you can do it across multiple texture images at the same time, going across each other, blending them together with this multiplier add. We'll get into some more of this in the next video. We start playing around with mathematics and textures and such with this, so it's very cool, very powerful. Okay, a lot of fun too. It gets into some creative, fun stuff you can do with all this. Okay, so with that, let's have a look at what we can do here. So we have out.color equals diffuse color times text 2D, and this comes back with the actual texture. Now, if you remember, color sampler is getting the color pixels from the image. It's sampling individual pixels from the image. Remember, this is going to be spread out across the whole 3D card, and so after all these vertices have been computed, it's going to move over to the pixel shader, and it's going to compute all the pixels at the same time on the 3D card, and simultaneously processing these pixels. So the pixel sampler is going to grab an individual pixel, you know, this coordinate x, y here, or UV, let's be a little more accurate, UV here, and it's going to apply that pixel to that place on the model. That's it. Well, actually, to render to be the screen space here. But yeah, and then we have our texture coordinate, so where it's going to appear on the model, and then this is kicked back here on the out to be outputted as a color to be displayed here on the screen as such. And that's what's happening, more or less. So again, mapping a pixel to the image texture coordinates, just like you saw back here in Blender with the plane, mapping pixel to the coordinate system on the actual model. So that's what we're doing here with that sampler. 2D sampler with the in.text coord with the 2D text function. That's what that function does. The color sampler gets the pixel, and then the texture coordinate is applying that pixel to the texture coordinate on the 3D model to be rasterized. By multiplying this color through here, that gets into the math color theory. Just watch that video series for that, and then you'll see all the information about how that works. And then return out kicks back out this color to be again applied to the texture. And we're able to get away with using the exact same technique here, technique 0, and pass P0. Here we're still using cold face enable equals false. Vertex program compile VP40. We're still using that profile. Everything's exactly the same from before. Alright, and that is texture, how to apply a texture to a 3D model in a material, and doing the UV coordinates and the and mapping the pixels, the pixel shader and the vertex shader together. And again, just to show you, have a little more fun with this. We can absolutely, it's just so cool, man. It's so neat having where you can sit there and easily just manipulate the color to be multiplied times the texture to make it do all kinds of crazy stuff like that. Alright, so thank you for watching. This has been Nate Nestler for Hyperactive Studios, and thank you very much. Enjoy the next video.